On Tuesday, December 24th, Christmas Eve, the Parker Solar Probe will make history once again. It will come within a staggering 6.1 million kilometers of the Sun, the closest distance any human-made object has ever achieved. This moment marks the spacecraft's 22nd orbit around our star, part of its groundbreaking mission to complete 24 orbits in total by the end of its journey. Launched in 2018, the Parker Solar Probe is not only the fastest human-made object ever built, traveling at an astonishing speed of 6,900,000 kilometers per hour, but also the most daring. It is venturing into the Sun's outermost atmosphere, the corona, to uncover secrets that have eluded humanity for centuries. As it approaches the Sun on this record-breaking flyby, it will communicate back to its team on December 27th. Once it has moved far enough from the Sun's intense heat and radiation to establish a stable connection. Nick Binkine, the mission operations manager at the Johns Hopkins Applied Physics Laboratory, summarized the anticipation best. "No human-made object has ever come this close to the Sun. We're thrilled to reconnect with the spacecraft once it emerges, feeling invited home." In this video, we'll explore how the Parker Solar Probe is pushing the boundaries of human exploration. From its incredible speed to its daring maneuvers, this mission is redefining what is possible in space exploration. Stay with us as we delve into the story of this groundbreaking spacecraft and the awe-inspiring science behind its record-setting journey. The Sun, a colossal ball of hot plasma, is the foundation of life on Earth. Its surface, known as the photosphere, is a searing 5,500 degrees Celsius. Yet, strangely, the Sun's corona, the thin outermost layer of its atmosphere, reaches temperatures exceeding 1 million degrees Celsius. This dramatic increase in temperature, as you move farther away from the Sun's core, defies the laws of traditional heat transfer. Scientists have long wondered, how is this possible? In our everyday experience, heat flows from hotter regions to cooler ones, gradually dispersing energy. This principle, rooted in physics, makes the Sun's temperature gradient seem almost magical. How can the Sun's outer atmosphere, so far removed from its nuclear furnace, be hotter than its surface? The answer lies in the Sun's magnetic fields, which twist, tangle, and snap in ways that produce extraordinary bursts of energy. Magnetic fields on the Sun are generated by the movement of charged particles deep within its interior. These fields rise through the surface, forming loops and arcs that stretch into space. Over time, these loops become entangled, like strands of spaghetti in a boiling pot. When they cross and reconnect, a process known as magnetic reconnection, they release immense amounts of energy, potentially heating the corona to its staggering temperatures. This process was once purely theoretical. For decades, scientists could only observe the Sun from afar, using telescopes and satellite imaging. But these methods, while valuable, could not provide the detailed, direct measurements needed to confirm how magnetic energy heats the corona. That's where NASA's Parker Solar Probe comes in. By flying closer to the Sun than any spacecraft before, the Parker Solar Probe is gathering critical data that allows scientists to test these theories. It is revealing how the Sun's magnetic fields behave at a scale we've never seen, offering unprecedented insights into the mechanics of magnetic reconnection. The temperature mystery of the corona is not just a question of scientific curiosity. Understanding why and how the corona becomes so hot has practical implications. The same processes that heat the corona also influence solar wind and space weather. These phenomena can disrupt satellites, interfere with GPS systems, and even cause power outages on Earth. By solving the puzzle of the corona, scientists are laying the groundwork for better predicting and mitigating these effects, ensuring that we can continue to rely on our technology in an increasingly interconnected world. As the Parker Solar Probe dives closer to the Sun, we are inching closer to unraveling this mystery. The findings from this mission are not just reshaping our understanding of the Sun, but are also providing a blueprint for understanding other stars across the universe, where similar magnetic phenomena may be at play. The corona's secrets are slowly being revealed, illuminating the intricate and powerful forces that govern our Sun and, by extension, our solar system. The Parker Solar Probe is a remarkable feat of engineering, designed to endure the Sun's extreme heat and radiation, while venturing closer to our star than any spacecraft in history. Launched in 2018, this groundbreaking mission marks the first time humanity has reached into the Sun's atmosphere, entering regions long thought to be beyond our reach. Named after Dr. Eugene Parker, the scientist who first theorized the existence of the solar wind, the spacecraft embodies the culmination of decades of scientific ambition. To achieve its extraordinary mission, the Parker Solar Probe is equipped with advanced technologies that allow it to survive and operate in the Sun's hostile environment. At the heart of its design is a cutting-edge heat shield made from carbon composite materials, capable of withstanding temperatures of over 1,370 degrees Celsius. Behind this shield, the probe's instruments remain cool and protected, enabling them to function even as the spacecraft plunges through the Sun's corona. These instruments include a suite of tools specifically designed to study the Sun's magnetic fields, plasma, and high-energy particles. The field's instrument measures electric and magnetic fields, mapping the Sun's dynamic magnetic activity. Whisper, a powerful imaging system, captures detailed pictures of solar wind and plasma structures. Another key instrument is Double East, adding devices for massively correct magnetic patterns and allowing whisper images of the solar wind. Grant learned the actual mind of the instrument includes its hardware and algorithms, specifically designed to study the solar wind and plasma structures. Another key instrument measures electric and magnetic activity. Whisper, a powerful imaging system, captured allotments keeping agents from altering the Sun's orientation to the rotation of the Earth. Together, these tools provide a comprehensive view of the Sun's outer layers and its complex magnetic environment, giving scientists unprecedented access to the forces shaping our star. The Parker Solar Probe's journey to the Sun is as extraordinary as its mission. To achieve its close approach, the spacecraft uses a series of gravity-assist maneuvers, flying past Venus multiple times to adjust its trajectory. Each flyby tightens its orbit, bringing it closer to the Sun. In November 2024, the probe executed a record-breaking flyby of Venus, passing just 234 miles above the planet's surface. This maneuver allowed it to reach an astonishingly close distance to the Sun, just 3.8 million miles. At this proximity, the Parker Solar Probe shattered records, becoming the fastest human-made object in history. Traveling at a staggering speed of 4,500 miles per hour, the spacecraft could circle Earth in just over 3 minutes. This incredible velocity allows it to plunge deep into the Sun's corona, gathering data in a region no other spacecraft has explored. In this way, the purpose of this mission is not just to demonstrate technological prowess. The Parker Solar Probe is designed to answer fundamental questions about the Sun that cannot be addressed from Earth or from a distance. By directly measuring the environment where the solar wind originates and where the corona's intense heating occurs, the spacecraft provides invaluable insights that could not be obtained otherwise. Cassie went on. Each orbit brings the Parker Solar Probe closer to the Sun, and with every passage, it collects data that is transforming our understanding of the star that sustains life on Earth. This mission is more than an engineering triumph. It is a testament to humanity's relentless curiosity and determination to push the boundaries of what we know. The Parker Solar Probe has not only broken records, but also unraveled mysteries about the Sun that have perplexed scientists for decades. With each close pass, the spacecraft sends back groundbreaking data, painting a clearer picture of the Sun's dynamic behavior and its effects on the solar system. Among its most significant discoveries are insights into the Sun's magnetic fields, the heating of the corona, and the acceleration of solar wind. One of the most fascinating findings is the phenomenon known as magnetic switchbacks. These are sudden and sharp reversals in the sun's magnetic field, observed in the solar wind. These magnetic kinks are not random. They originate close to the sun's surface in regions of intense magnetic activity. The Parker Solar Probe revealed that these switchbacks are likely caused by magnetic reconnection, a process where tangled magnetic field lines snap and reconnect, releasing bursts of energy. As these switchbacks travel outward, they transfer energy to the corona, playing a crucial role in its extreme heating. Another breakthrough came from understanding the role of helium ionization in the corona's high temperatures. On the sun's cooler surface, helium atoms lose only one electron, allowing them to release energy as radiation. But in the superheated corona, helium atoms become fully ionized, trapping heat and enabling even small amounts of energy to drive the temperature to extreme levels. This discovery highlights how relatively minor energy inputs can lead to the corona's intense heat, solving a key piece of the temperature mystery. The probe has also shed light on the structure and behavior of the solar wind, the stream of charged particles flowing outward from the sun. It found that magnetic switchbacks are more common in areas with open magnetic field lines, those that extend into space, compared to closed loops that arch back to the sun's surface. This suggests that open field lines play a significant role in transferring energy and accelerating solar wind particles, providing new insights into the mechanisms driving the solar wind. Perhaps one of the mission's most celebrated milestones was the direct observation of the Alfvén critical surface, a theoretical boundary where the solar wind disconnects from the sun's magnetic influence and transitions to supersonic speeds. This was the first time a spacecraft had crossed this boundary, offering unprecedented insights into the transition between the sun's corona and interplanetary space. These findings are more than just academic achievements. They have practical implications for predicting and mitigating the effects of space weather. Solar storms, driven by the sun's magnetic activity, can release massive amounts of plasma and radiation, which can disrupt satellites, interfere with GPS systems, and even cause power outages on Earth. By clarifying the processes behind solar wind acceleration and corona heating, the Parker Solar Probe is helping scientists refine models to better forecast these events and protect our technology-dependent world. Each discovery made by the Parker Solar Probe not only advances our understanding of the Sun, but also provides a foundation for understanding other stars across the universe. Similar magnetic and plasma processes occur in stars of all types, as well as in phenomena such as stellar flares and black hole accretion disks. By studying these processes up close in our Sun, we are gaining valuable insights that extend far beyond our solar system. The Parker Solar Probe is proving that the Sun, with all its power and mystery, can no longer hide its secrets. With each orbit, this mission brings us closer to understanding the forces that shape our solar system and the cosmos beyond. The discoveries made by the Parker Solar Probe are not just unraveling the mysteries of the Sun. They are shaping the future of science and technology in profound ways. By exploring the Sun's corona and magnetic fields, the mission is paving the way for advancements that will protect critical systems on Earth and enhance our understanding of the universe. One of the most immediate benefits of the Parker Solar Probe's findings lies in the realm of space weather prediction. Solar storms, driven by the Sun's magnetic activity, can release powerful bursts of plasma and radiation that travel across the solar system. These storms have the potential to disrupt satellites, damage communication networks, and even cause large-scale power outages on Earth. By studying how energy and particles are accelerated in the solar wind and corona, the probe is helping scientists refine forecasting models. With more accurate predictions, we can better prepare for and mitigate the effects of geomagnetic storms, ensuring the safety of our technology-dependent infrastructure. The probe's insights into magnetic reconnection and plasma dynamics are also advancing our knowledge of universal phenomena. Magnetic reconnection, observed on the Sun, is the same process that drives other cosmic events, such as stellar flares, magnetar eruptions, and even the behavior of black hole accretion disks. By observing these processes up close in our Sun, scientists can apply these findings to distant stars and celestial bodies, creating a deeper understanding of the forces that shape the universe. Another key area of impact is the study of the heliosphere, the vast bubble of solar wind that surrounds and protects the solar system from harmful interstellar radiation. The Parker Solar Probe's measurements of the Alfvén critical surface have provided new insights into how the solar wind transitions from the corona into interplanetary space. This understanding is essential for refining models of the heliosphere's structure and its role as a protective shield for Earth and other planets. The mission is also contributing to our ability to design future spacecraft capable of exploring extreme environments. The engineering breakthroughs behind the Parker Solar Probe, such as its heat shield and radiation-resistant systems, set a precedent for developing technologies that can withstand the conditions near the Sun or even in other harsh regions of space. These advancements open the door for missions that could explore the Sun's poles or venture even closer to its surface. Beyond its practical implications, the Parker Solar Probe inspires a sense of curiosity and wonder. The Sun is not just a source of light and warmth. It is a laboratory for understanding the physics of magnetic fields, plasma, and energy transfer. Every piece of data collected by the probe connects us to a broader narrative about the workings of the universe and our place within it. As we decode the Sun's behavior, we are also gaining a better understanding of the stars that populate our galaxy. By studying the Sun up close, the Parker Solar Probe provides a template for studying the life cycles and dynamics of other stars, helping us piece together the story of how galaxies evolve over time. The implications of this mission extend far beyond its operational timeline. The Parker Solar Probe is not only protecting our modern world from the risks of space weather, but also unlocking knowledge that will shape humanity's exploration of the cosmos for generations to come. While the Parker Solar Probe has already revolutionized our understanding of the Sun, it is not working alone. Collaboration is a cornerstone of modern space exploration, and in the case of solar science, the Parker Solar Probe's mission is complemented by another trailblazing spacecraft, the European Space Agency's Solar Orbiter. Together, these missions are painting a more complete picture of the Sun's complex behavior and magnetic environment. The Solar Orbiter, launched in 2020, offers a different perspective on the Sun. While the Parker Solar Probe dives deep into the Sun's corona, the Solar Orbiter takes a broader view, capturing high-resolution images and studying the Sun's poles, regions that are difficult to observe but critical for understanding its magnetic cycle. The combination of close-up data from the Parker Solar Probe and wide-angle imaging from the Solar Orbiter is providing an unprecedented look at how the Sun's magnetic fields evolve and interact across different regions. Any known Earthling with a sensible distance sensor. This partnership is not only helping scientists understand the Sun's present behavior, but also paving the way for future missions. The Parker Solar Probe's daring close approaches and groundbreaking discoveries raise new questions that could shape the next generation of solar exploration. For example, are there additional mechanisms contributing to the extreme heat of the Sun's corona? How do magnetic switchbacks evolve as they travel outward through the solar system? And what do these findings mean for stars beyond our own Sun? Future missions may build on the success of the Parker Solar Probe by venturing even closer to the Sun or targeting its poles, where much of its magnetic activity originates. Such missions could provide deeper insights into the Sun's 11-year magnetic cycle, which influences solar storms and other space weather phenomena. These efforts would further refine our ability to predict solar activity and protect Earth's technological systems. On a larger scale, the discoveries made by the Parker Solar Probe and Solar Orbiter are expanding our understanding of stars across the universe. The Sun is a relatively average star, Yet the processes observed in its corona and magnetic fields are thought to occur in stars of all types. By studying these phenomena in our Sun, we are gaining valuable insights that could be applied to the life cycles of stars, the formation of solar systems, and even the conditions that make planets habitable. The Parker Solar Probe's mission also demonstrates the power of international cooperation in space science. The sharing of data between NASA and ESA not only enhances the scope of what we can learn, but also exemplifies how nations can work together to achieve ambitious scientific goals. This collaborative spirit will be essential as humanity tackles even greater challenges in space exploration, from understanding other stars to exploring distant planets. As the Parker Solar Probe nears the end of its mission, its legacy is only beginning to unfold. The data it has collected will fuel research for decades to come, inspiring new missions and sparking fresh questions about the Sun and the universe. While we may never fully unravel all the mysteries of our star, the Parker Solar Probe has brought us closer than ever before, illuminating the path for future discoveries. The Parker Solar Probe has redefined what is possible in space exploration. By venturing closer to the Sun than any spacecraft in history, it has broken records, shattered long-held scientific assumptions, and opened new avenues for discovery. From unveiling the mysteries of the Sun's corona to directly observing the Alfvén critical surface, the probe's findings are transforming our understanding of the Sun's behavior and its influence on the solar system. Through its groundbreaking data, the Parker Solar Probe is helping scientists predict space weather with greater accuracy, ensuring the safety of satellites, communication networks, and power systems on Earth. Its insights into magnetic fields and plasma dynamics are also contributing to our understanding of stars and celestial phenomena across the universe. Like the echoing sound of Parker's solar probe across the universe. Working in tandem with ESA's solar orbiter, the Parker Solar Probe represents the best of collaborative science, proving that when nations unite for exploration, the possibilities are limitless. As its mission nears completion, the data it has collected will continue to inspire and inform generations of scientists, sparking new missions and questions about the forces that shape our universe. The Parker Solar Probe's journey is a testament to human ingenuity and curiosity. It reminds us of the boundless potential of exploration, urging us to look beyond the horizon, toward the stars, and into the very heart of our solar system. While the Sun still holds many secrets, the Parker Solar Probe has brought us closer to understanding its mysteries, paving the way for discoveries that will shape the future of science and technology. Stay curious and keep exploring, as the story of the Parker Solar Probe is far from over.